Welcome to Aerotech's Automation1 motion control platform educational series. Aerotech is a company that solves your toughest precision motion and automation challenges. Automation1 is a motion control platform consisting of software-based controls and development tools, PC and drive-based control hardware, and hardware-based drives for servo motors and other devices. In this video, we'll take a look at setting up and using infinite field of view in Automation1. My name is Chris Charlesworth, and I am the European Control Systems Engineer for Aerotech. We'll start with what is infinite field of view. Aerotech's infinite field of view is a unique, industry-leading solution for the synchronization of linear and rotary servo axes with laser scans. Infinite field of view produces significant throughput improvements and eliminates stitching errors and part quality issues due to overlapped and mismatched laser processing. You can find out a lot more information and a full feature overview on the website. We're going to focus today on the configuration and the system setup of this and the basics of how to use it. We will first have a look at the hardware setup needed for infinite field of view. On the screen currently is a simple block diagram of a system. This in particular is one of our demonstration systems, but it's applicable to any system where infinite field of view may be used. We have the GL4 on the right hand side, which is the laser controller itself. We have two servo drives, the XC4Es, and they are used to control our two stages. In this particular case, it will be an XY stage from the ANT130 range. Now, as you can see, the XY drives connect to the XY stage. The GL4 will connect to, in this case, a 2-axis laser scanner, and then we have what are called sync cables between the servo drives and the galvo drive. Here are some pictures of our system. So this is one of our demo systems at the UK office. On the right hand picture we have the stages that we're going to move. So at the bottom there's an ANT XY underneath a platter. You can see there's a white sheet of paper on there. Then you can see one of our AGV 14 HPOs attached on top. There'll be a red laser attached to that as well. We've just got a laser pointer, but of course in an industrial system that would be a much more powerful laser than this one. On the left we have the actual drives and the hardware. Here's a close-up view of the hardware. At the top there we have that sync connection. Now this connects from the two servo drives to the galvo drive. This is very important as it allows the position feedback to be transmitted to the GL4, which allows for the advanced servo loop capabilities and for all the error correction and compensations to take place. You can see highlighted in the center there is the laser output connection. So we can have up to 3 outputs to a laser, which allow you to do different laser modes and to do some power correction and things. We've got our two servo drives on the left, the galvo drives in the middle, and then we have our control PC on the right. Now we'll move into Automation1 and we'll take a look at how to configure this system. We'll now have a look at how to set up and program the laser motion and the system as a whole. We'll begin by going through a few verifications we need to do about the motion directions. We'll take a look at some of the key parameters that we need to set up. Then we'll move on to the actual programming and a demonstration of how IFOV can be programmed very quickly. We have our system here, and on the screen in front of you, you can now see part of the window is the Automation1 Studio. You can see we've got 4 axes enabled, and on the right hand side is the webcam that we have attached to the demonstration system. The first thing we need to do is check that the axes have been set up in a collinear fashion. So we're going to pair the GX and the X and the GY and the Y in the infinite field of view algorithm. Now what's crucial is that these axes move in the same direction. In this particular case, you can see there's a red laser spot on the screen. That's coming through the infinite field of view. This is just a laser pointer that we pass through to be able to do demonstrations. And now if we jog the X, the GX axis in the positive direction, we can see the red dot moves across to the left hand side of the screen, and we're moving away from our little crosshair in the center. Now if I take the X axis, I want the X positive jog to move the laser spot in the same direction. So as you can see, we're getting further away from the X on the middle of the axis. Now, similarly, of course, when we move backwards, we can then reasonably expect this to move backwards in the same fashion. Then we also need to check that the y-axis does the same thing, so we can see moves away, the x is moving downwards, and now when we do positive y, the laser spot is moving in the same direction on the paper. So if you imagined a graph or a set of measurements, you'd be moving in the same direction on that graph, so you're always moving in the positive y for where that spot is on the paper. If they are not moving in the same direction, the simplest thing to do is to change the direction of the servo axes. To do that, the fastest thing to do is to go into the machine setup and then click through to the connectivity, and then you can invert axis just here, and that will do all the internal settings. You can do this manually as well, but it's easier and far quicker to do that from there. If we have a look in this, you can see there's a reverse motion direction under the motion category. If I just hit the X on that, we'll go there just to demonstrate this in action. So we'll just turn these back on. We'll turn our laser spot back on. And we'll do it to the Y, as the Y is the one that's furthest away. So you can see I'm moving it positive at the moment. If I reverse its direction and I do a quick reset, and if I move it positive again, now you can see that the crosshair is moving up on the screen. So that's reversed the motion direction. So there you go. That's the first thing you absolutely have to do before you do anything else. And this is, of course, once you've properly set up the system so all the axes have got at least some basic tuning in there. Now, let's talk about the encoder divider settings. Now, this is crucially important that it's set correctly, as any sort of mistake in this area will often give you a very odd reaction. Either the IFOV will appear not to work, or you may start hitting different limits as the IFOV tries to run through its algorithm. Here's a couple of things that you need to be aware of. The maximum quadrature output frequency of the Automation1 drive is 100 MHz. So that is where we've taken an encoder coming in, and then we converting that into a pulse stream to then be sent out to the IFOV algorithm in this particular case, but this also counts for the PSO. Now for this is the internal use only, so this is if you were going to go to the PSO function. The maximum frequency to output is 25 MHz. Now this is very, very important to understand. And there's a simple piece of math that we can do to establish whether or not we meet the requirement. So the maximum encoder frequency, which is just counts per second, is the maximum axis speed that you're anticipating multiplied by the number of counts per unit. You can grab the number of counts per unit out of the configure workspace. So if we hop into the configure workspace of Automation1 Studio, you can see I'm on the y-axis, and under the axes section, we have the units down at the bottom, and you can see the counts per unit in this case is 3,276,000. That's a very useful piece of information which will formulate our counts per unit. So our counts per unit, so in this case per millimeter, we have the 3.2 million. System move speed, we're anticipating up to 50 millimeters a second in this case. It's good to try and define an approximate maximum speed, and you can always put that into one of the thresholds so you can't exceed it. Now, for the number of counts per second, it's simple. It's 50 by 3.276 million, which in this case will be approximately 163 megahertz. That's too high for the output frequency in general, let alone the maximum encoder output frequency, which is only 25 megahertz. So then we need to divide that down. We could divide that by 10, 20, 30, 40. In this case, we're going to do a division by 20. So we found that that was very, very stable, and that gives us what we need to do. It also gives us a healthy amount of extra space just in case this system has to go faster than 50 millimeters a second. Something to bear in mind on this are some notes that are within the help file. So if you look up the device functions page, the web address is at the bottom, but if you just go into our help file and type in device functions, it'll bring you to the main page. It's quite far down the page, but there is a note about the drive encoder outputs. So it's very, very important that you take a quick look at this section, and you can see there is a full explanation of this. There's also something to be aware of, that if you're using a sine wave encoder like I am, then you need to use the primary emulated quadrature divider parameter to ensure that the system configures correctly, and then we would set the drive encoder output divider to 1, as we will do today. We'll now take a look at the settings that we need to configure within Automation1, but to begin we will look at the machine setup just to run through how we have our system configured. So in the first couple of pages it's already been set up. We've then got the electrical devices, so we have a GL4, we have two XC4Es. Mechanical devices, we have an ANT130XY and an AGV14. Then on our interconnectivity, we've got the first XC4E is the X-axis, and that's in millimeters. On the second XC4E is the Y-axis. And then we've got our GL4 where we have GX and GY already set up. You can also see here that we can invert these axes if we need to, and that may come in handy later. On this last page is where we normally set the parameters. In this case we're not going to do that, as these are quite special parameters that are already in there, all the tuning that's been done on the setup work, so we're just going to exit without saving. Up in the controller section of the configure workspace, you've got the IFOV option. It's very important to set this up. Without setting this, it won't tell the controller it's going to do infinite field of view. Number of configurations, we can have up to 2. We only want the 1 today. We can also set our IFOV maximum time. Normally it's 250. On this system it's been set to 500 due to some different testing that we've been doing. Next thing to do is we need to tell the different drives where they're going to receive their inputs. So what we have is the XC4Es will output their encoder data, and that will be received into the GL4 via the sync cables. So under the feedback section of axes in the configure workspace, we have the X and Y, and we have the GX and the GY, which are our galvo axes. On GX and GY, we need to go to the feedback setup parameter, and then we need to just click on the pencil and you can see the IFOV input down here. Now we need to set them for sync port A for GX in this case, and for GY it is sync port B. There you go, sync port B. The reason for that is that we've now told the GL4 where it's going to receive the IFOV encoder input, and that's going to be from our servo axes, which it will then use as part of the calculations for the infinite field of view algorithm. Setting the output from the XC4Es and some of the other settings is all done programmatically, and we'll have a look at that in a moment. The only other thing to mention is going to be what we call the encoder input divider. When we look at the X and the Y, in this particular case we used a sine wave encoder with a feedback resolution after multiplication that was very, very high. We're looking at approximately 300 nanometers. If we were to output this from the XC4E, even at a low speed, we would likely overload the permitted encoder channel frequency. So what we need to do is just scroll down here, and then we can have a look at the primary emulated quadrature divider. Now, if we click into this, we can take a look at this sort of in the help section. But what this allows us to do is to, instead of say outputting at 200 megahertz, it allows us to separate it down, to divide it down a little bit into a more manageable value. And in a second we'll take a look at a calculation of how we arrived at this number. So you can see I've got the X set to 20, and I believe I have the Y set to 20 as well. Those are the parameters that need to be set in order for IFOV to be able to work. Now let's look at the Aeroscript program that's needed to set up and use the infinite field of view. There's about 10 lines needed to set up this properly. This is one of our demonstration programs. This will draw the Aerotech logo on a 50 by 50 grid, so we'll demonstrate that a little bit later. The key thing to do first is to set up the drive encoder output. So we've just been discussing the divider. Well, this is where the other side of that has to happen. We use the drive encoder output configure input command. And now what this will do is it will set the output channel on the XC4Es and give them all of the output. Now that we've discussed the divider settings, we'll have a look at the Aeroscript commands needed to set up and use the infinite field of view. There's about 15 lines, and it's really all the same no matter how many IFOV systems you might create. They all have the same basic setup. First things first, we need to set up the encoder outputs. To do this, we need 3 commands for each of the drives, so in this case we've got 6 commands. To start with, we'll use the drive encoder output configure input command. Now what this will do is, for each of the XC4Es, so that's the x-axis, it will set up the output channel, which in this case is sync port B. That's where we've plugged our sync cable into, and we will transfer it the encoder input channel of the primary encoder. Now these are all done with enums, so we'll just demonstrate quickly how this is set up. We'll choose the x-axis, we'll choose the encoder output channel. You can already see I've hit E and it's already bringing up the appropriate enums for me. I'm just going to highlight this and press the dot. We want to use sync port B in this case, so we'll select that. And then we want to choose the input channel for that. Again, this really does fill itself in, so it's all very, very simple. All these enums are already set up. Something to always note is where it says as and suggests something like encoder output channel, it's likely that that's going to be an enum, at which point it's much quicker to program. We'll take that out. We then have the drive encoder output configure divider command. Now in this case, as I mentioned, we're using a sine wave encoder. We've already set up this divider inside the parameters. So we're just going to set these to 1 for the sake of completeness, but they do default to 1, so you could omit this from the code in our default system. Then we also have to turn on the drive encoder outputs. So in this case, another very, very simple command. Choose the axis, which channel are we going to turn on, and then what output mode are we going to use. Just to show you the output modes we have here, if I take this out, we only have quadrature at this time, but there are other options that may be available in the future. The next thing we have to do, we set up the infinite field of view. So we'll scroll down a little bit. First thing we need to do is set up the axis pairs. Now you'll notice that all the commands for IFOV start with IFOV, so it does make it very, very easy to go through the system. First thing we have to do is set the axis pairs. Now in this case we've got the GX and X on the first array, and then we're going to do GY and Y. Now if you look up this command in the help file, you will see that we always put the Galvo axis first in these pairings. We then have the option to set a scale factor. I have in this case, and the instructions of how to do this are in the help file, but quite simply what I've done is taken the count per unit on the GX axis, the count per unit on the X axis, divided one by the other and multiplied by 20, and this takes out the scaling factor that the divider gives. So it's just a small correction there. The next thing we do is set up the IFOV set sync axes. Again, not entirely necessary because this command is only really used if you want to synchronize another axis. In this case, we're not going to. We then set the IFOV size, and we set the time. So this is to set the look ahead. The set size of the field of view is 100 millimeters, and the set time in this case is how far the look ahead is going to operate. So we're operating at 300 milliseconds in this case. And then we set the acceleration and tracking speed. In this case I've chosen 5,500, but you could have that higher or lower. When I first set up this system, I had it set very low. I had it set to about 50 on the tracking speed and 500 on the acceleration. I then sort of played with the system and increased it. There you go, that is actually it. That's it for setting up the infinite field of view. The other thing we have to do is then set up the laser output. In this case, I'm just using a static laser. It's nothing special. We just do a PSO output, configure output, GX, and tell it it's going to be the GL4 laser output 0. Again, you can see it's an enum to make life easy. And then I just turn it on in this case. And the final thing to do is to turn on IFOV. You can see at the top of the program, just for completeness, I always turn off the IFOV while it goes to the configuration, and it's also at the end of the program as well. Last couple of things we do, turn on things like velocity blending and set up the task modes, but all this also happens as part of the way we can recommend programming this. The really quick way we're going to do it today is to show CAD Fusion generating this code for us. So I've opened CAD Fusion and I've opened up a project that I already had. In this case, it's just the Aerotech logo. Now, I imported this as a DXF. If you go up to File, you can start a new project, or you can actually go to Import, and you can go, okay, import as a new Automation1 project, and then choose a DWG or a DXF file. What that will do is just import it straight into CAD Fusion, and then all I had to do was select the shape and move it over the origin point. So in my system, the origin is in the center. So I wanted the logo to be centered over it, and then I just scaled down the logo to make sure it would fit within the space. The other thing we've done here is I selected everything, went to Project and hit Optimize Project. I just left everything as it was. What this will do is then organize everything into individual shapes. And in this case, I also applied skywriting. What the skywriting will do is allow the laser to sort of flick off the shape and smoothly come back round to flick back onto the shape. We were creating this to move very, very quickly, so this often gives a better dynamic profile. We're not going to focus too much on CAD Fusion, I just wanted to explain what we've done. Everything's already been set up. In the project settings, we've named our axes, GX and GY. The lovely thing about the IFOV is we just command the laser and the servo axes get taken care of. You can see we put in a bit of skywriting and we've put in some initial values for the motion feed rate. It will suggest some to start with. I increased them on this one. And then we have a default tool, which in this case is the PSO tool. That's quite important, and I'll very, very quickly demonstrate how to set up a simple tool. If we hit Catalog and Catalog Manager, we can then look at adding a new tool. In this case, it's a PSO tool. And it goes, yes, it's called PSO tool. What sort of PSO type is it going to be? In this case, I just set it to toggle the output, but you could have it doing pulsing, you could have it doing different window modes if you wish to. You can set the drive type and things in here as well. And what this allows you to do is just set up where it is, what's going to happen, and then all this code gets generated for you. So if I just go back into here, you can see the PSO tool. If I press edit, you can see, oh, I used asynchronous, so it's continuously turned on. It's coming off the GL4, I've attached it to the GX axis, and then I've said PSO wants to turn on after the lead in move and turn off after the lead out move. There's lots of different settings in here. Once that was done, File, Export, and then the Aeroscript program that you can use pretty much straight away is right here. What you can also do in the project settings is put in initialization and termination code as standard. So you could write this and then give it a file, or you could just type the code in as you wished. That would allow you to then generate a full program each time. All I've done is then copy this file, and you can see in this case I've used Aeroscript language. I could also set it for G-code, and then it turns on and off the tool, and it also puts in lots of comments so you understand what's happening in your program. All I had to do from there is just copy this straight into the workspace, and then I just moved a few things around. So in this case, I moved the hash defines up to the top, and then I left everything pretty much as it was. You can see this root group, layer all these, they're all from the CAD Fusion, and during the setup as well I just made sure everything was all working nicely. So there we go. That's a very simple, very quickly written program. If we bring the camera back up on the screen, we can then play this and then you'll see exactly what's happening. So there's a quick homing routine, and then the system will run through. Now I've already added in some app data collection things. If I go into the visualize workspace, you can see we drew the logo. Now my test program doesn't have the skywriting in there, but there you go. That concludes this motion control platform educational video. Thank you for watching. I hope you enjoyed learning about setting up and programming the infinite field of view with Automation1, with also a quick look at the CAD Fusion.